In this example, we're looking at a mixture of three gases, and we're given the mole fractions of each gas. Pressure is 2 bar, temperature is 100 degrees C, and what we're going to do is cool down this mixture, and gases A and B can condense, but they don't mix in the liquid phase, so when they condense, we'll eventually have two liquids and a gas in equilibrium above them. And we want to know what this looks like in terms of plotting partial pressures. So on this graph, what we want to plot is the partial pressure versus the temperature for each of the species. And we can start out by, when we first cool down, we don't see any change in the partial pressures because we're above the saturation pressure. So let's look at the pressure of B. So the pressure of B is the mole fraction of B times the total pressure. Mole fraction is 0.6, total pressure 2 bar. So this is 1.2 bar. That's the partial pressure of B. As we cool down, it stays constant. Likewise, for A, the partial pressure is 0.6, and let me just pause and write. Now the other thing to point out is the pressure of B at this condition, 100 degrees C, so this is, we start 100 degrees C. Pressure B is less than the saturation pressure of B, which is 1.5 bar. Same thing true for A. And then the pressure of nitrogen is here. So pressure of nitrogen, again, mole fraction of nitrogen times the total pressure, and the mole fraction is 0.1 times 2 bar. So the partial pressure when we started nitrogen is 0.2 bar. So something to point out, as we lower the temperature, we're going to lower the saturation pressure. And in this problem, we have this, if you like, artificial condition that they have both A and B have the same saturation pressure, 100 degrees, and they have same heat of vaporization. So when you look at the Clausius-Clapeyron equation, it means at all temperatures, they're going to have the same saturation pressure. And that just makes it easier to make this graph for this problem. So let's look at what happens when we get to a point where we've lowered the saturation pressure because we've lowered the temperature, and we start condensing out B. Now we only condense out B because A and B don't mix in the liquid phase. B has the higher partial pressure, 1.2 bar, so at this temperature, the saturation pressure of B is going to be 1.2 bar, and so we're going to start getting condensation. So let me pause and just plot how that might change. We don't know the heat of vaporization, so we don't know the actual temperature scale. So as we continue to lower the temperature, we continue to lower the saturation pressure, and so more B condenses, which means since the total pressure is constant, the pressure of A must increase, the partial pressure. And so I picked a point where now A and B have the same partial pressure. And so at this point, since B is already at its saturation pressure, now A will be at its saturation pressure. And if we do the calculations, and we'll look at that later, then this pressure for A and B, so at this point, pressure of A equals pressure of B, and that's 0.857 bar. Well, as we're lowering the temperature and condensing out B, we also have to increase the partial pressure of nitrogen. So let me plot that. So then the question is, what happens now as we continue to lower temperature? Now we're lowering the saturation pressures of both A and B. So we condense out both of those species. The pressures follow each other since their heats of vaporization are the same. Their saturation pressures are the same at each of the temperatures now. So we condense out both liquids. Let's look at what that plot might look like. I've just picked an arbitrary point where the pressure here of A and B is 0.68 bar. Well, it turns out then the pressure of nitrogen is 0.64 bar. Pressures have to add up to 2 bar. Let me draw in that. You notice now pressure of nitrogen increasing more because we're condensing out both species. And at all conditions, pressure of A plus pressure of B plus pressure of nitrogen equals 2 bar. When we're in this region where both species, A and B, are condensing, then this is pressure of A plus pressure of A. And now the pressure of nitrogen, right at this point, just when they're ready to condense, so the pressure of A and B are the same, the mole fraction of nitrogen is 1/3 the mole fraction of A when we start, and it remains 1/3 the mole fraction of A up until the point where A starts condensing. So when B is condensing, both mole fractions increase, and that's because the mole fraction was 0.3 for A at the start and 0.1 for nitrogen. So this is 1/3 the pressure of A. And what this means then, that point pressure of A, 0.857 bar, that's how we get the number that we put here. So we've drawn the plots that tell us how, as we lower the temperature, species condense, how the partial pressures of each of these components change.